Assalamu alaikum, dear ITU family. This is Dr. Mohammad Mahbooba Rahman. I am an assistant professor with Electrical Engineering Department of ITU. At ITU, I had the Wireless Solutions Research Lab. My research lab focuses on many interesting problems. For example, resource allocation for 5G and beyond systems, physical layer security, smart grid communication, nanoscale communication involving molecules for communication, or the traditional wireless-based solutions in terahertz band. Today, I'm going to share a talk with you, which I recorded for IEEE VTC 2018 Fall Conference. And that work was done by my MS student. And the broad area is smart grid communication. Please listen to it and ask me questions if there are any. Um, Finally, an important announcement before my talk commences. If you guys are looking to do a PhD at ITU, please get in touch with me. I have multiple open PhD positions in my research group. Enjoy the talk. Thank you.
Hello everyone, this is Dr. Mehboob from Information Technology University, Lahore, Pakistan. This work has been carried out by my MS student Shah Hassan. So here comes the outline of my talk. First, I want to motivate the context of this problem. Specifically, the people in power systems community, they are interested in detecting power imbalance. The power imbalance arises because of the mismatch between the instantaneous load demand and the generated power. The sole measure of power imbalance is the deviation of grid frequency from its nominal value, which is 50 Hertz in Pakistan and 60 Hertz in the US. So the grid frequency deviation is the sole indicator of power imbalance. So by means of this grid frequency deviations, the grids typically employ a phenomena which is called frequency control. And what does this frequency control do? It brings back the grid frequency to its nominal value whenever there is some deviation. We consider a very simplistic model where we have multiple generators, but they are serving only 3 loads, and the load could be a medium load or a light load or a heavy load. So this allows us basically to model the grid frequency time series as a Markov chain with 3 states. In the end, I'll provide some results, and finally I'll conclude and provide some pointers for the future work. So what exactly is the frequency control? As I briefly discussed before, whenever there is a power imbalance in the grid, it's typically detected by means of grid frequency deviations. So why is this the case? It's because of this classical relation that the grid frequency deviation is directly proportional to power imbalance. So how are the grid frequency measurements obtained? They are typically obtained by means of either the phasor measurement units, or more recently by means of a frequency disturbance recorder. And once we have these measurements are utilized by the so-called frequency control mechanism, which I explained before. There are 3 tiers of control: the primary control, secondary control, and tertiary control. The primary control is mainly about adjusting the speed of the motors and adjusting the amount of fuel intake so that the generation power is either reduced or increased in response to the fluctuating load. The secondary control, on the other hand, it works on a different time scale. So here comes the experimental data we obtained from NPCC Pakistan, and this kind of tells us that the frequency control is actually enforced by all the grids. So this time, if we look at these plots closely, then we see that for the first 100 minutes, the grid frequency, the instantaneous grid frequency, which is plotted in the top plot, it stays mostly negative, and which means that we need to increase the generation power. So this is what the the frequency control does. If we look at the bottom plot, then we see that the generated power increases continuously for the first 100 seconds. And if we once again look at the instantaneous grid frequency values in the top plot for the last 400 minutes, then we come to know that the grid frequency deviation is mostly positive, which means that now the power is surplus. So somehow the load has decreased. So then once again the frequency control comes into the action, and we see that for roughly last 400 or 350 minutes the generation is continuously decreasing in order to reduce the cost of generation. So now coming to the system model. So we have a very simplistic system model where we have X generators and we have just 3 loads. The default setting is where only load 1 and load 2 are on, and this is the scenario of medium load, and the power is generated so that it's matched to the load. So when the system is in the state of medium load, the generation and the load power are matched, so there is no frequency deviation. And then we have the scenario of the light load where we switch off the load 2, so only load 1 remains active. That means now the generation is surplus. So that so how to see that? So when we take the grid frequency measurement in this scenario, then we will see a positive frequency deviation. And finally we have the state of heavy load where all the 3 loads are switched on, and since the power, the generated power is matched to this case of medium load by default, so in the case of heavy load the generation power will be short compared to the load demand, and we can see that by means of frequency deviation, which will be negative. All in all, this simplistic system model allows us to model the true grid frequency time series as a Markov chain with 3 states. But as I hinted before, the true grid frequency can never be known. We only make noisy measurements by means of PMUs or FDRs. So because of the noise in the grid frequency measurements allows us to model the true grid frequency as a hidden Markov chain, and the hidden Markov chain here on this slide is represented by SK. So we can see there are 3 states in the hidden Markov chain: -1, 0, +1. -1 means that there is a negative frequency deviation. 0 means there is no frequency deviation, and +1 means that there is a positive frequency deviation. And now we also see a Markov chain on the top as well, which is labeled as XK. It also has 3 states. So what's the difference between SK and XK? SK are the states of the hidden Markov chain, which is the truth, but we cannot get to know that. XK is what we observe. So in our case, what we do hypothesis testing on the grid frequency measurements, and the outcomes of the hypothesis test, they give us the XKs. So let's go to the next slide. So here are the details relevant to the hypothesis testing. So you might want to notice a diagram on the right side. So that diagram is it kind of shows a trimodal density which has 3 Gaussian random variables as its components. So it's kind of a mixer density. So the message we want to convey here is that basically there are 3 kind of load situations as I described before: the medium load, the low load, and the high load. And because of slow or inefficient frequency control, there could be a situation that apart from the main lobe, 2 side lobes which are colored green and red, they might arise. So what we do here for hypothesis testing, we just pass our measurements ZK to a maximum likelihood test, and it simply measures the distance of the measurements ZK with 3 ground truths which are denoted as MI, Basically, as I said before, we know that we have three discrete loads here. So we know the MIs. So those serve as the ground truth. So with the ground truth known, the ML decision rule is simply a partition of this probability space on the right side of this diagram into three regions, and accordingly the xk, which is basically the observed Markov chain, it could take values either -1, 0 or 1. So the performance of hypothesis test. The hypothesis test, it could incur two kind of errors: the false alarms and misdetections. What does a false alarm means? That means there was no frequency deviation, but the hypothesis mistakenly declares that there is a frequency deviation, and accordingly the frequency control mechanism basically adjusts the speed of the motors to increase or decrease the generation. So that is harmful. And what's the misdetection? That means there was actually a great frequency deviation, either positive or negative. There was a mismatch between load and generation, but somehow we decided that there is no mismatch. So that will also lead to some cost. And since the grid frequency measurements are assumed to be Gaussian random variables in this case, so that leads to all the error probabilities being the Q functions. The Q function is basically the complementary CDF cumulative distribution function of a standard normal random variable. So next, now we want to outline the essential ingredients of the hidden Markov model. The hidden Markov model is completely described by means of two matrices, P and R. P is the so-called transition probability matrix, which kind of tells us that how a Markov chain is actually evolving over time. And what's the matrix R? It's called the emission probability matrix. And if we look at the definition of the entries of matrix R, then we get to know that all the entries on the main diagonal of matrix R, these are actually the correct detection probabilities of the hypothesis test I have described in my previous slide, while all the off diagonal entries of matrix R, these are actually the error probabilities. So therefore, now we know that all the elements of the matrix R, they could be written in the form of Q functions. And one more thing here to notice is that the P is a right stochastic matrix, which means that if we sum the elements within each row of P, that will be 1. And similarly, the matrix R, it's left stochastic, which means that the sum of the elements within each column of R is 1. So now, having described the hidden Markov model setup, how to proceed further, we proceed further by means of maximum likelihood sequence estimation. In the short form, we call it MLSE. And MLSE is a tough problem to handle. Therefore, it's typically solved by means of a Viterbi decoder, which does MLSE iteratively by forming a trellis graph. So let me tell you the essential details here. So basically, we want to maximize the joint density. So that's our objective function, which we want to maximize. And the joint density is between a sequence or a vector x and the sequence s. Remember that the x represents the observable Markov chain, which is actually the outcome of the hypothesis test, and S is the hidden Markov chain, which cannot be observed. So what we do here, we split the joint density into the product of a conditional density and a marginal density by means of a Bayes rule. And if we look closely into the expanded expression of the conditional density, then we get to know that the conditional density could be constructed by means of the elements of the matrix R, which is the emission probability matrix. Similarly, if we look closely at the expanded expression of the marginal probability PS, then we get to know that this marginal probability, it could be constructed by means of the elements of the matrix P, which is the transition probability matrix. So with this, we are now ready to discuss the results we have. So as I said before, if we want to compute the MLSE using the Viterbi decoder, all we need to know is the knowledge of matrix P, matrix R, and pi 0. What is pi 0? It contains the probabilities of the system being in some state at time 0. So in our case, we have 3 states. So we want to know so what was the prior probability of the system when we basically started the system. So here we have provided P matrix and R matrix, and if we look closely at the P matrix, the entries are designed in such a way that all the transitions away from state 0 are discouraged and all the transitions towards state 0 are encouraged. That means that is kind of reasonable, because that tells us that the frequency control mechanism is in force. So matrix R, it depends upon Q functions, as we saw in the previous slides. Therefore, if we want to look at matrix R, so we have to plug in so many different parameters, and then we get one such example. Coming to the results. First, we have a result on hypothesis testing. So we have 2 plots here, actually plots the detection correct detection probabilities against SNR. How do we define the SNR? SNR is defined as the inverse of the standard deviation of the measurement error. So high SNR means that the measurements are more and more reliable, and we see that there is a kind of cutoff point that for both plots, if the SNR is greater than 12 dB, then the detection probability for both cases is almost 1. That means the hidden Markov model becomes more and more visible when the SNR is increased, and vice versa. But if we look at both figures from right to left, that when what happens when SNR is decreased, so we can see that when SNR is decreased beyond 12 dB towards 10 dB and 5 dB and 0 dB, then the impact of the low quality of measurements is more on the case of unequal periods. So that's why there is a need to improve further on the performance of hypothesis test. We do that by means of MLSE, so which is solved using Viterbi decoding. So what we have done here to get this plot, we actually plot the accuracy, the histogram of the accuracy. So what exactly is this? So we have 2 histograms. The green histograms are the represents the accuracy of the hypothesis test. The blue histogram represents the accuracy of Viterbi algorithm, and we can clearly see with the naked eye that the blue histogram is shifted right compared to the green histogram. So that tells us that the hypothesis test, that tells us that the Viterbi algorithm is performing better than the hypothesis test. And if we want to quantify it, then we get to know that the mean accuracy of the Viterbi algorithm is at least 5% greater than that of hypothesis test. So that brings me to the conclusion. So as we saw in the previous slide, that the mean accuracy of Viterbi algorithm is at least 5% greater than that of hypothesis test. That leads us to conclude that hidden Markov model is kind of an effective model for true grid frequency time series. Thank you all for listening, and if you have any questions, comments, you can send me an email to mehboob.rahman@itu.edu.pk. Have a good day.